welcome to today's class. I want us to look at half-life of a radioactive material. And we can quickly look at it so we can define half-life of a radioactive material as the time taken for a radioactive material to decay to half the original number. Or we can always say that yes, it is the elapsed time taken for a radioactive material to reduce to half the original number. For example, if the number of atoms initially present is N0, the time taken for it to reduce to half is what we refer to as half-life. Now, of course, if it reduces to half, we now have, this is a new element now, the one is remaining. This one will decay. So time taken for this one to decay, and this one will now have half of the original one. Is what we refer to as half-life. Now, this half-life can be represented by the equation T half. So T half, it can give us the representation of half-life. And then it is equal to natural logarithm of 2 all over the decay constant, lambda. Now the SI unit of half-life, it can be in seconds, it can be in minutes, it can be in year, day, week, depending on the element. And of course, we know that yes, different elements decay at different rates. So the time taken for an element to decay is what we refer to as it. So now the SI unit can be in seconds, it can be in seconds, it can be in minutes, it can be in days, it can be in months, it can be in year. So certain elements decay or they disintegrate at different times. Now that will now take us to the decay constant. Of course, the decay constant is nothing but proportionality constant in a decay law. Of course, if you make a decay, so we say where lambda is the decay constant, the decay constant. Now, this decay constant can now give us, if we make decay constant the solution to the formula there, this equation will now give us to natural logarithm of 2 all over the half-life. And of course, the natural logarithm of 2 is 0.693 all over T half. So we can now have that, yes, the decay constant is given as that. And of course, it is the inverse of this this half-life, which would now give us that the SI unit is if this one is in minutes, it cannot be in per minute, or if this one is seconds, so it can be in per second, it can be in per minute, it can be in per day, as the case may be. It can still be in per year, or in per month, or per week, as the case may be. Now, the next thing I want us to look at is the decay law. The decay law. The decay law, which will now give us that N is equal to the initial number of course, this one is the final number. What is the initial number or initial quantity, initial mass of a radioactive element? Now, it is we now have this exponential function minus raised to power minus lambda t. So we now say where n is the, let us start with this n0. n0 is the initial number of atoms present, initial number of atoms present. Initial number of atoms present. Now this n here, n is the final number or the final mass remaining after the decay. So which will give us, so we now have this as the final mass remaining, final mass or final number of atom after disintegration. After the disintegration. Now lambda, of course, this lambda, both lambda and t there is negative. So just from the decay curve, if we're assuming we have the decay curve like this, where this is t in second, this one is n. Now the curve will now give us like this. So at any point, you can always get, so if this is the initial number, so which is n naught, if we have n naught here, so we can always trace this and then trace it down. The time taken is t1, corresponding to n naught. Now the next one that will decay will now give us, we can have here, and half of this one, and half all over t2. Now if we take this one now, this one will now give us like this. So this is a t3 corresponding to half of n over 2, which will give us, and for as the case may be. So when I have that here, so it is that negative sign because it is decreasing exponentially. So when I have that, this is the decay constant, lambda is the decay constant, and of course we have given the SI unit. The next one is the time. T is the time of transmutation. We can say time of transmutation. Time of transmutation, or time taken for the decay process to continue. Remember, each element, because the nucleus are unstable, they disintegrate. So in order to achieve stability. So this T there is the time of the transmutation and not the half-life. Okay. Now, having taken this, we can now look at some problems we will now solve using this. There are a lot of problems we can solve. Basically 1, 2, 3. Now in our next video, we shall look at how these equations are being derived. But for now, let us concentrate on the calculation. However, this one here, having reached the n, which is the final mass, this is the initial mass, and then this is the exponential function, and then we have this. There are so many ways of solving half-life related problems. So let us look at, we will be moving. Question says, iodine 131 has a half-life of 8 days. If there are 200 grams of this sample, how much of iodine 131 will remain after 32 days? Now, solution. We have that the element in question is iodine 131. Now, the original number of its element is 200 grams. That is the original mass. Now, the half-life there is 8 days. Now, time of transmutation, time taken for the whole changes to occur is 32 days. And the question now is, what is the mass of the iodine 131 that will remain after this? So, of course, this is unknown. There are basically two ways. There are different ways of solving this problem. I will solve it using two different formulas. Now, the next one is, since the original number is 200 grams, so we now have it here as 200 grams. This is alternative 1. 200 grams. Now, after 8 days, 200 grams will decay. Now, after 8 days, these 200 grams will decay, and half of it will now be 100. Now, after another 8 days, this 100 will decay, leaving 50 grams. After another 8 days also, 50 will decay, and 25 will remain. So this is 8 days. Remember, total time taken must give you 32. So 8 plus 8 is 16. Plus 8 is 24. Now it means that after another 8 days, 25 would disintegrate, leaving half of 25, which is 12.5 grams. So this is the mass that will be remaining after these 32 days. Alternatively, we can still solve it another way to get exactly that number using decay law. So alternative 2, we can use using decay law, using that decay law that gave us that n is equal to n naught exponent negative lambda t. Now, we have, this is what we're looking for, the number that is remaining. This is the original mass there. Lambda is not given. This is time of transmutation, which is 32. So let us get this lambda. So for us to get the lambda, which is the decay constant. Decay constant, recall that we said that decay constant is equal to natural logarithm of 2 all over the half-life. Now, which will now give us that natural logarithm of 2 is 0.693 all over half-life. Half-life is 8 days. Therefore, the decay constant will now give us 0.693. 0.693 divided by 8 will give us 0.0866 per day. So per day. Now, having gotten that, we substitute into this, and we will now have, this is the original mass that is remaining, our mass left. Original mass is 200 exponent negative lambda. Lambda is 0.0866 multiplied by time. Time of transmutation is 32. So which will give us 200 exponent negative. Now 0.0 times 32. The whole of this will now give us minus 2.772. Now exponential of this 200 times, of course, the exponential function, you know how to get the exponential function, just press shift and then min, natural logarithm. So which will now give us minus 2.772. The exponential of this function will give us 0.0625. Now multiply this by this. 200 times 0.0625. It will give us 12.5 grams. So this is the mass that is remaining. So using any of the ways can go. Either you work it out like this. So this is the grams. Work it out like this, or you can still do it using this decay law. Now we'll take the next question. This one says, a radioactive substance has a half-life of 3 days. If a mass of 1.55 grams, if a mass of 1.5 grams of this substance is left after decaying for 15 days, determine the original value of the mass. Determine the original value of the mass. Now, this is the mass that is left, which is a N naught, and we want to determine the original value. The decay constant was not given, and then from here, they said the half-life has a half-life of 3 days. That means the half-life there is 3 days. Now, the time of transmutation is given to be 15 days. It took 15 days for a certain mass to, let's say, X, to reduce to this. Okay. Now, the question now is, what is the original number that is left? Okay. Remember, this question says, now we can quickly look at use decay law. Now, if we use decay law, because this one now we're not going to use the other one because they didn't give us the original mass. Okay, so we now have n equals n naught exponent negative lambda t. Now this lambda here, which is the decay constant, not given. The transmutation time given to be 15. So we'll look at this straight. So we now have lambda is natural logarithm of 2 all over the half-life, which will give us 0.693 all over the half-life. Half-life from here is 3 days. Therefore, the decay constant will give us 0.693 divided by 3. Will give us 0.231 per day. Now we now come back to this equation and say, since we're looking for this, we now have the mass remaining is 1.55 equals n naught exponent negative lambda. Negative lambda, our lambda is 0.231 multiplied by time of transmutation, which is 15 days. If we do that, we have 1.55 is equal to n naught exponent, now minus 0.231 multiplied by 15 will give us 3.465. Now 1.55 is equal to n multiplied by exponential function of minus 0.34. So which will now give us minus 3.465 will give us 0.0313. Now this will now give us, if we make n not the subject here, we now have 1.55 all over 0.0313. Now the original number there will now give us 1.55 divided by 0.0313, and we will now get 49.52 grams as the original mass. So what it is that this mass now, an element having this mass as an initial mass with this as the half-life, having decayed for 15 days, now the fraction remaining is this. Okay, now we'll take the next. This one says a radioactive nuclide of mass 6 grams has a half-life of 8 days. Calculate the time during which 5.25 grams of the nuclide have decayed. Calculate the time during which 5.25 grams of the nuclide have decayed. Now, solution. From this, we now have that original mass n naught is 6 grams. Now the half-life is 8 days. The time during which, now this T is what we are looking for. During which this N, this mass of 6 grams, have decayed to, during which X have decayed. The decay there is 5.25 grams have decayed. Now remember, this one has decayed. This one has decayed. And that decay law says N is equal to N naught exponent minus lambda T. N naught is the original number. This one is the mass remaining. Now, if this is the original mass, this one has decayed. What the question we'll ask ourselves is, which one is remaining? What is the mass remaining? Therefore, we now have, for you to get N will give us N naught minus this one that has remained, that has decayed, which is 5.25. And which will now give us N is 6. Therefore, 6 minus 5.25 grams. The one that is remaining there is 6 minus 5.25. If this has decayed, what is remaining now is 0.75. So 0.75 grams is what is remaining. Now, like we solved the first one, we are going to solve this same way we solved the first one. Now, if this is the number of the original mass remaining, the original mass, now after 8 days, 6 will decay and 3 will be remaining, half of 6. Now, after some time, after 8 days again, this 3 will reduce to half, which is 1.5. After another 8 days, 1.5 will decay, and 1.5 over 2, 1.5 divided by 2, 1.5 will remain, 0.75. So this is a fraction that will remain. Two of them are in agreement. So we now have that, yes, total time of transmutation now, time of transmutation will now give us 8 times 3, 8 times 3, which will give us 24. So 24 days is the time remaining. Okay, the time taken for this element to reduce to that. Now we can solve it using this equation. So alternatively, if we use this equation, N is equal to N naught exponent minus lambda T. Now we are going to look at we are going to find lambda first. After that, we'll now come here. Now, for us to get lambda is natural logarithm of 2 all over the half-life. And then the half-life there is, half-life is 8. So we now have that lambda will give us 0.693 divided by 8 will give us 0.086625 per day. Remember, this one is days. It's per day. Now, we now have this. Remember, we're looking for this. Since we're looking for this, we can bring these two together. So if we bring these two together, we'll now have N all over N naught is equal to exponent minus lambda T. And in this case, to take care of this exponential function, we need to remove it. Now we take the natural logarithm of both sides. So we have lim this is equal to lim this. And if we now take this, this one will go. Therefore, we now have natural logarithm of n over n naught is equal to minus lambda t. Minus lambda t. Now, which will now give us ln n. N is this is what is remaining, 0.75 all over the original mass. Original mass is 6, which is equal to minus lambda. We have gotten our lambda to be this, minus 0.086625 multiplied by t, is t. Now, we'll now take this, we'll come back here and say natural logarithm of 0.75 divided by 6 will now give us natural logarithm of 0.125 is equal to minus 0.086625t. Now, if we take the natural logarithm of this number, natural logarithm of 0.125 will give us minus 2.079, which is equal to minus 0.086625t. Now, make t the subject. T will give us, I'll write it on top, I'll clean here. So if we clean here, we'll now have that t will give us, of course this minus will take care of, if you divide, that minus will go. We'll now have 2.079 all over 0.086625. Therefore, the time of transmutation will give us 2.079 divided by 0.086625. The transmutation time will give us 24 days. Therefore, alternative 1 gave us 24 days, and alternative 2 still gave us 24 days. Anyone that is convenient for you, please do what to use it. Remember, in exams, we don't award marks for taking a very long journey. We award marks for getting the right thing. Now, we'll take the next one. So, any formula that is easier for you, please follow that one up. Now, take this question. And this one says, if the fraction of the atoms of a radioactive material after 120 years is 1/64, what is the half-life of the radioactive material? What is the half-life of the radioactive material? Now, they said if the half-life, if the fraction remaining after, one is 1/64, that is the fraction remaining. Now, they said the time for the transmutation, T, is 120 years. Now, the question says, what is the half-life? What is the half-life? Now, the half-life, for us to get the half-life, I will use just a simple method to solve it. Now, the original number is n. Now, after one half-life, it reduced, n reduced to n over 2. Now, after another half-life, I will continue to reduce n until I get this fraction, 64. Now, that is the best way to solve it. Now, have n over half of n over 2 times half will give us n over 4. So I will now have over 4 here. Now, after another half-life, this one will decay, and half of this will now remain, which is 8 times this is 4 times 2 is 8. So this one will decay, n over 8 will remain. After another half-life, we have over 8 times half, 16 here. So when I have 16 will remain. So this is the half-life. Now after another half-life, we continue. After another half-life, this one will decay, and n over, of course, this is if you have 1 over 16 times half, will give us n over 32. So this one will decay, n over 32 will remain. Now after another half-life, this one will decay, n over, if you half of this one will now give us 64. And of course, this is the fraction, this is the desired fraction. Now the next thing we'll now do is we'll calculate all the half-lives. If we calculate all the half-lives, we'll now have, so we say total half-lives. Total half-lives is equal to 1, 2, 3, 4, 5, 6. So I have 6 half-lives, 60 half. We say, but the transmutation took place. It took place in 120 years. In 120 years. Therefore, we equate this. So we now have 60 half is equal to 120 years. Let T have the subject. T half will now give us 120 over 6. 120 over 6 will give us 20 years. So the half-life here is 20 years. Now we will still take more questions. Next one. This one says the half-life of a radioactive material is 6 hours. What quantity of 1 kg of the material would decay in 24 hours? What quantity of the radioactive material would decay in 24 hours? So we now have that half-life of radioactive material. So the half-life there is 6 hours. Now, original number is 1 kg. The original number is 1 kg. Now they said what quantity of the material would decay? The one that would decay, X would decay in 24 hours. The transportation time there is 24 hours. So what quantity would decay? Remember, the decay law says N is N naught exponent minus lambda T. So this is the original mass. This one is what will, this is the remaining, the mass remaining. But in this case now, they want mass that will decay. So what we'll do now is we'll find N. After getting our N, we now subtract subtract N from the original number. That is where we now get the mass that will decay. So in other words, we have this. They did not give us, we'll put this as question mark. So since we are given this, no lambda, we'll find the wavelength. Sorry, we'll find the decay constant. Now the decay constant is natural logarithm of 2 all over 0 all over T half, which is the half-life. It will now give us 0.693 all over T half. T half is 6. Therefore, the decay constant will now give us 0.693 divided by 6. We now have that decay constant is 0.1155 per hour. Per hour. We say per hour. You can say H raised to power minus 1 per hour. Now, having gotten this, we'll now go back to that equation to say N is equal to N naught. N naught is 1 kg times exponent of minus lambda 0.1155 multiplied by time of transmutation, which is 25. Now we now have n is equal, and of course one times is still 1. So we'll now look at exponent minus. So this times that 0.1155 times 24. Everything will now give us exponent 2.772. Okay, n will give us exponent of this value, which is negative 2.772. Exponent of that will give us 0.0625. Okay, this 25. This is the, of course, this is grams. This is the mass that is remaining. To get the mass that have decayed, we'll now say n naught minus n will give us x. Therefore, x is equal to n naught 1 minus 0.0625. Therefore, the quantity that have decayed will now give us 1 minus 0.0625. So the one that is that have decayed is 0.9375 grams. So this is what is remaining. Alternatively, we can still solve the other way around, but we continue to do that, our time will continue to increase. If you use the other formula, we can still get this. So what it means, so total transportation time there is 24. So if we use the other formula, this is n naught, and of course n naught is 1. So what it means that 1 after 6 hours, 1 will reduce to half. So after another 6 hours, this one will decay, and this one will decay, and we'll have 1/4 will remain. So after another 6 hours, this one will decay, and we'll have 1/8. Now after, this is 6 plus 6, 12, 18. After another 6 hours, this fraction, this one will now decay. I will have 1/32. So this is the one that is remaining. So the one that so mass decayed will give us 1 minus this. Sorry, this is 16, please, because 2 times this will give us 16. So this is the quantity that is remaining. So the one that is decayed, this side have decayed. So we'll now say 1 minus this, 1 minus 1/16, which will give us, of course, this is over 1. LCM of 1 and 16 is 16. Now, 1 into 16 is 16. 16 times 1 is 16, minus 16 into 16 is 1. 1 times 1, this. So which will give us 16 minus 1 will give us 15/16. Therefore, and this 15/16 is this fraction. So we have, so this is the fraction that have decayed. This is the fraction remaining. So we should always take note of this. The last but not the least, we'll take this one. This one says, calculate the half-life of a radioactive sample with decay constant 2.1 times 10 raised to the power minus 2 per second. Okay, solution. This one is very simple. And if you get this type of question, do not panic. So they said, calculate the half-life of a radioactive sample Now this radioactive sample, they gave us the decay constant. They say that the decay constant is 2.1 times 10 to the power minus 2 per second. So if this is the decay constant, remember the relationship between half-life and the decay constant. We say that half-life is equal to the natural logarithm of 2 all over lambda. So which will give us natural logarithm of 2 is 0.693 all over the decay constant, which is 2.1 times 10 to the power minus 2. And of course, you can put this in ordinary form, which will now give us 0.693 divided by 0.021. These and these are the same. So which will now give us 0.693 divided by 0.021, which will now give us 33 seconds. 33 seconds. Okay. This is where we bring the lesson to an end. Please, if you have not subscribed to this channel, do well to subscribe to this channel. Hit the subscribe button and then turn on the notification button so that each time I drop a new lesson, you will get notified. But if you have subscribed, please just give me a thumbs up if you find this lesson interesting. Thank you very much. See you in my next lesson, where I will be treating nuclear energy and a nuclear reaction. Thank you.